videos recorded on it for this class that I was going to post, and just like Hillary, I have no idea where they are. So, well, I wasn't being investigated and then
really
decided to delete them.
Or...
Somebody has my videos. I just don't know who. So if anybody found a thumb drive in here.
Probably WikiLeaks or whatever.
WikiLeaks has my emails. I mean my videos. Man. Alright. So you should finish up taking the quizzes and reading in chapter 4. Alright, so chapter 4 is talking about linear structures. So structures where we have sort of one thing after another. And the only things we really care about are adding new things in some manner, right? Either sorted, or always adding to the beginning, or always adding to the end, or adding to the beginning and take away from the end, right? So we got our first in, first out, which is a queue or a linked list where we maybe always push things at the beginning, right? And we always take things off of the end, right? So that the first thing that comes in, just like a line of McDonald's, is the first one that gets out. We've got our last in, first out, which is our stacks, right? So the last plate that you put on a pile of plates is the first one that you take off, right? And then you can implement solutions such that you can do any of those types of operations. So any questions on the linear structures? Right, we should know a few properties about them as far as runtime. So, if you're adding something to the beginning or end of a list and you don't have to traverse the list, right, we have constant time. If you need to search the list for something, what type of time is that? End time, or as the chapter is titled, linear time, right? So that we call that linear if we have something like, n time. Right? That's linear. Or n over 2, right? How long does it take to insert something? On average, n over 2, right? Worst case, n every time. So any questions on this? I got lots of no's and yeses. Any questions? You guys got a homework, so I'll ask about that. How's the homework going? Questions on the homework?
Yeah. Okay, so let's say the user option to either push or pop is entering a digit 1 or 2. Okay? But why when validating, like when the user put in, is like, why does ABC make it just go crazy? Like it just keeps running the same thing. Like it won't let me type anything after that.
Why does ABC go crazy? Yeah, so part of the deal is that you're dealing with. Yeah, so it keeps you're probably in a loop and you aren't updating the fact that you need to reread a new character.
Okay.
So that could be one. So some of the easier ways to do it is to try and do the conversion on ASCII. Right, so read it in as a string, and then use A to I on that.
Okay.
And then assume that 0 is not something that you would have in your menu.
Okay.
Right, because 0 means either it could be a 0 or it could be I couldn't parse this thing. Does that make sense? So why don't we do an example? So let's say I have an array of characters. Right, so 0 gives us 0, but also flat or whatever, right, characters will give us 0. So just assume that we're not allowing 0 to be entered as a string. So then you can use 1, 2, 3, and then you can do a switch on it. Other questions? Recalling that I will not be here tomorrow.
What time is the deal Wednesday?
I think it's 11:59.
Yeah, it's like 11:59 at night, I think.
Not ready for the other class, but I was doing turning in homework for it. I didn't see anything on Blackboard for it.
I put a Dropbox up. It should be due by tomorrow. Or no, maybe it's tonight. So that's in 402, right? Yep, there's a Dropbox for that. I made it last night. If there is issues like that, just send me an email, because somebody sent me an email, so then I created it because I had forgotten to create it. So
I figured so I just wanted to
okay. Other questions? Issues? Troubles? Good jokes? How many people are done? 0. How many people started? I know 1. Okay, most people started.
So it says create a menu that allows the user to select, just like how technical you want it to be.
The menu could be, please enter 1 to add something new, enter 2 to do something, to pop off,
Okay.
right? And when you add something new, it should allow me to type it, right? The dotted quad should add it to the list. If you want to help yourself, you can make a print so you can see what's on the stack. Right? It shouldn't be too hard to do. That probably would help you verify that you are indeed pushing what you want. But that's up to you on that one, I believe, right? I don't think I said that in the document. Also, make sure that you handle the case where you've deleted everything from the list. I know that can be an issue, right? So if you push on, 3 things and you try to pop off 4, right? How do you handle that issue? How do you add when the pointer might be null if you have that? So make sure you test those cases.
That's what your ringtone reminds me of.
My what?
Your ringtone.
Oh. What does it remind you of? Something. All right, so no more questions? Going once? Going twice? Sold to the lowest bidder. All right, so I think we're going to, for the moment at least, skip chapter 5. We'll go straight to chapter 6. All right, so chapter 6 is going to talk about binary trees. So thus far we've talked about a structure which is linear in the sense that we add things in sort of a one-dimensional manner. So we're going to start talking about binary trees. So binary trees are we create a data structure such that we have basically a tree-like structure, and they use kind of weird words. So if you think about a tree, right? So when we talk about a binary tree, we talk about this thing called the root, which I guess if we were like thinking of it as a tree and the top of it and this part was a root and you had stuff sort of growing from it, it's like a tree that's growing backwards, I don't know, right? So the root is going to be the node where you're going to start at. And then the root node is going to have sort of 2 things where we call children, right? So we very creatively named them left and right.
Okay, before we do this,
Yep.
In our whatever book, it's chapter 7 and chapter 6's design.
Oh, is it?
Yeah.
Okay. I stand corrected. Chapter 7, binary trees. Chapter 6 and
I just wanted to make sure.
yeah, I'm just using this one because I don't have to frickin' log in, and you can just click on crap.
Sticks to landing.
I got some skills. So chapter 7, not 6. All right, and then we can talk about things like if we have a particular child, right, or a particular node in the tree, we can talk about the descendants, right? So the descendants of node C would be E, F, G, H, I, right? So all of its children, all of its grandchildren, right? So we talk about things like that, right? Aunts and uncles. No, we don't talk about aunts. I guess they just talk about uncles. I don't know why they don't talk about aunts, but talk about uncle, right? Like your brothers, your dad's brothers, right? Stuff like that. We can talk about ancestors, right? So for a particular node, if we have its ancestors, so for example, node E, its ancestors, you basically trace back up the tree, right, and get each parent until you have hit the root node. Right? So the root is the top, always the top, and if we're talking about binary trees, there's only a left and a right, right? So binary means, right, we've got two choices, right? So does this kind of make sense? We can talk about the depth of a node, right? So they talk about depth. So depth is how many, how far do you have to go to get to a particular node? So if we look at the root, the depth of it is 0, right? I have to do node traversals in order to find it. If we look at C, it has a depth of 1. G has a depth of, how many nodes do I have to traverse to get to it, starting at 3? What?
2, 3.
You can't count?
1.
Okay, somebody else besides him, because he clearly cannot count.
What was that?
You're bad at throwing. So if this is 0, this is 1, this is
That's what we get breakish.
3, right? 0, 1, 2, 3. That's the depth of 3. Now we also have this notion of a child or a node in the tree that has no children is called a leaf node, right? Again, with the tree analogy, right? So we have a root, and we have leaves growing at the bottom, and this is like a backwards tree, right? It's growing upside down. Maybe gravity is different for it. I don't know. That's just weird. I would think the reason why people draw it this way is because it's easy to sort of start drawing, right? And you're like actually drawing a picture and draw it down, because that's how we do stuff, right? We can talk about a path, right? So a path is a sequence of nodes that we visit in order to get to a node, right? So the path to get to node G is going to be A, C, E, G, right? So that would be a path, right, where we traverse nodes inside of the tree. Okay? And there's a couple questions. So,
Hey, I've got a question not necessarily pertaining to this.
okay?
So, this
Question.
is purely hypothetical.
Purely hypothetical.
Yeah, I know
Clearly not an
anyone,
actual thing. Okay.
yeah, who would ever do this. But would it be against UNK's policy if someone were to hypothetically build a web scraper, scrape the website, maybe use a module such as Selenium to answer the questions after it's scraped?
You're saying a lot of things.
If somebody were to automate the process of scraping, hypothetically automate the process of scraping pages.
I'd be more proud than anything.
Well, that's probably true. I don't think there is any fault in doing that if somebody were to do that. Now, if somebody were to, say, automate the process of submitting these and then hand it out to other students, clearly that is a violation of.
Okay. Purely hypothetical. I'm not going to. I just wanted to know.
I feel like any sentence starts off with, is it against UNK policy?
Well, yes.
Is it against UNK policy? Not that I know of.
Yeah. Well, I built a module to automatically submit homework just because I'm tired of Blackboard. So,
Spencer hates Blackboard, so then he comes to me and asks, like,
Yeah.
a similar question to this hypothetical question about submitting stuff to Blackboard.
Yeah.
Because that's just how Spencer rolls, I guess.
Exactly. If you can automate it, why not?
Huh.
I'm not.
If only.
I promise.
All right. So here they're going to talk about a recursive data structures. So typically we're going to talk about defining data structures in a recursive method. So if we think about, so recursive just means that you're going to do some function, and then inside of that function, you're going to call itself, but typically with a little bit different data. So, for example, when we wrote our linked list, if we look at, for example, the print, right? So print, I just wrote an algorithm where it had a loop where it would print something, right? So to print off some text, right? If current wasn't null, it would print off some text. And then it would go ahead and update the pointer that it had for this current item. So we could take this print method and we could change it from an iterative solution, right, a solution where we iterate over something, to a recursive solution. So recursive just means that we're going to call the same function with a little bit different data.
Will it use the same amount of memory?
Will it use the same amount of memory? Okay, so here's the deal. There's a great benefit as far as programmer ability to reason about something if you write it recursively. So for a programmer, it is much easier for you to understand something that is recursive. Even though you're going to look at this and say, Dr. Miller, I totally don't get why we would want to write this recursively. There are a lot of problems that you can solve writing recursively that are much easier to write because you don't have to keep track of where you are and unwinding and things like that. That being said, it will take up more memory to write something recursively because every time I call that function, I am pushing a little bit of data onto the actual program stack. And because I'm pushing data onto that stack, I am using up memory. So eventually, right, we'll end up, if we don't know sort of the bounds on how big our data structure is, if we don't know that it's, for example, a linked list with 1 billion things, right, is going to fill up your RAM if you're going to try and do a recursive solution on that. But if you know I only have 10,000 things and I know I have this much RAM, right, you can go through and run a test and you can verify that. So there are pluses to recursion and there are minuses. Now the good thing is that you can take any algorithm that is recursive and you can change it into an iterative solution. Right? So there is a set of steps you can run through where you say, oh, I figured out how to do it this way. You can basically rewrite the code such that it is a iterative solution. So you can get rid of that Stack Overflow problem, right, where your stack just keeps growing until it runs into your heap, and then, right, stuff crashes, right, bad stuff happens. It's a good question. So let's say that I want to convert this print function from a iterative solution into a recursive one. So I'm basically just going to change this part to say if current is not null, right, I want to print the thing that I have. All right? And then instead of saying current is equal to current next and putting it inside of a while loop, I can say, oh, now does this make sense? So I print off the current data, and then I go ahead and call the print function on the next one. Right, so I'll print off my current data, and then I'll get the next one. Right, so this is a recursive solution. Now, there's not a lot of benefit in this one for doing this. Right? I have the same number of lines of code. exactly, right? Still have 3 actual lines of code. But it still works, right? Holy cow, that's a long thing. If only there was like a way I could do this. Okay, maybe there is. And if we recall, in this one, right, we had 3.14, and then we added the 4.5 and 5.6. Right, so this is the beginning of our list was at the beginning of printing, right? And the 5.6, which is the last thing, was at the end. But one of the cool things is that, so I can take this, and if I just reverse where I call it, so now if we look at this, right, I'm going to go and print the next thing before I print the current thing. Right, so I'm calling print before I'm actually printing off the data. So how is this going to print the list compared to the last one? Backwards, right? So it's going to, right, it's going to visit a node. It's going to go clear to the end of the list, right? And the last one we'll call print, the print function, and it'll do nothing, right, because next is null. So then it'll come back up one, print the last one, then print the second to last one, print the third to the last one. So now I've just reversed the way that my print works. Oh, got to recompile. So now we see that it prints the last one first, right, and the first one last. Does that make sense? Right? And when we look at the algorithm, it's really simple, right? This one is a simple one. But if we think about other algorithms that we've done, so for example, if you're going to insert something into a list, right? It's easy to write that as a recursive algorithm because you're thinking about, okay, I'm checking the current node, and if I don't find it, well, I can just call the algorithm again with the next one, right? So there are a lot of times where this recursive is going to be an easier way to solve our problem, right? So if we think about trees as a recursive algorithm, we could think about, well, let's assume that I was inserting a node into this tree. Well, if I know that it needs to either go on the left side or the right side, and we'll talk about reasons why it might go on the left or the right, we can just say, well, if it needs to go on the left or the right, I'll just call insert again, and I'll just go to one of the children, right? And then pretend like that's my new root node, and then go and insert again as a new root node, right? So each time, we're thinking of it as, oh, I'm going to insert, go down farther, I'm going to insert, right, until we get down to the bottom. Okay? Does that kind of make sense? Ooh. Math. Oh! Run away! See, when I hear run away, I think of Monty Python, but, Was it your mother was a hamster? She smelled of elderberry or something like that. Anyway. Okay. I think this is probably more fun. All right. So if we talk about doing a recursive, quit scrolling. Right, doing a recursive visiting, right? So we just talked about how we would go through and print them. Right, so we can do what's called pre-order, which is, right, so pre-order traversal is where you visit a node, right? So if you think about, we have this tree, right, that's like spread out. If we visit the root node, right, so pre-order is you visit the node and then you visit each of its children. So when I say visit, it's like print off, right? So I print off A, and then I visit each of its children. Well, if we're going to call this recursively, we're going to have 2 calls to the function. one of them is going to go before the other one. So I'm at A, right? And then I'm going to call B and then C, so I'm calling B. But that information that I'm going to call C is stored in the fact that I've got a recursive algorithm, right? And so the B is going to say, I'm going to visit, well, this one doesn't exist, right? I'll visit D, right? So we got A, B, D, right? And then we go down to C, and if we always are doing the left one first, right? C, E, G, right? And we come back up, well, this one doesn't have a child over here, right? E doesn't have a right child. F, H, I. Did I get it right?
Oh, I think I got it.
Does that make sense? Right, so pre-order is you visit the node first, or we print it, let's just say print it, right? We print the node first, and then we go and do each of its children. Okay? So that's pre-order. And it basically tells us how the binary tree is set up. Right? So if I have a pre-order traversal, I know where the root is, right? And then I can figure out what each of the children are for that.
Is there a special reason why we always go to the left?
Is there a reason why we always go to the left? Typically why we're going to the left is because we typically care about doing stuff in order, and we usually assume that the smallest things are on the left side. So we don't have to, but again, we would basically flip it if we wanted to do sort of the biggest things first, but typically we do the smallest things are on the left. That's just how that typically is. All right, so post order is kind of the opposite, right? We don't visit our root node until we visited each of our children, right? So we don't visit our current node until we visited each of our children. So we can see that we're going to start at A, right? And say, okay, let's visit each of our children. So I'm going to visit B and then C and then A, right? So I'm going to visit left and then right and then so, right? So, well, we're in D, we're going to visit its child to the left. Okay, I have a hard time with left and right, so you got to stay with me here.
You can't give me crap throwing. It was my right arm, I'm left-handed. But
I
you
can't
have
give you
no
crap.
excuse for that.
I can't give you. I can give you crap, but I don't know left and right really. I really don't know. Okay, so we try to visit the left-hand node of B, right? Doesn't exist. We visit the right hand, which is D, right? And then we visit B. Then we go back up to A. Well, I visited the left, now I got to visit the right. So visit C. Well, C says I need to visit my left and right, so we're going to go clear down here to G, which doesn't have any children. Then back up to E. Well, I got to visit the right hand of C, so I visit F, and then F, I got to visit H, and then I, and we go back up to F, and then C, and then A. Is that right? I think I got it right. So that's post order. So basically, pre-order and post-order are sort of opposites of each other, but they tell us information about how the tree is set up. Like, who is a child of who and how the tree is set up. And then we have what's called in-order traversal. So in-order traversal is where we're going to visit your left-hand children first, and then you visit yourself, and then you visit your right-hand children. You might say, why is this in order? So typically when we're setting up a binary tree, we typically call this a binary search tree. And there's going to be a property on binary search trees that is going to be very important to us. So let me draw it, because I think that's probably the best long-term solution, even though I delete all my videos, just like their emails. See, Hillary's email is just the joke that just keeps on giving. Okay, so the thing that we have with binary search trees is that we have the property that for a particular node, its left-hand side, all of the children on its left-hand side are less than its value. If we go with a strict binary tree. And all the children on its right-hand side are larger than it. Right? There are some trees where we can have nodes that have equal values, but we're going to take that out of the sort of equation at this point, right? We'll assume that if you have a value, that's how it's set up. So if we have a tree where we have a node of 20, right, and one of its children may be 10, and this one might be 22, right? Correct. I won't say right because that's bad. Maybe this is 15. 12, right? All right, so this is a binary search tree. So we have the property, if we look at it, right, everything to the right of 20 is greater than 20, right? Everything to the left of 20 is less than 20. And that property holds for every single node in the tree. So if we're looking at the node 10, right, I had to make sure that I did this right. I don't want to get in trouble. Right, everything that is to the right of 10 is greater than 10. Everything to the left of 10 is less than 10. So what does this, anybody think of what cool things we could do with this if we knew that everything that was to the left of you was less than you, and everything to the right of you is greater than you? What benefit could we get out of this? Well, it's called a search tree. Well, there's a reason for that. So why would it be beneficial when searching? Why would it be faster? Because you know where to look, right? That's true, right? So I know that if I'm looking for the number 77 and my root is 20, I know that, well, I can, if we have a tree that's sort of nicely built, right? I know that I can go on the right-hand side and look over there, right? Oh, look, it's magically there. But the thing is that you don't know that when you're looking at the tree, right? When I look at the tree, I don't know all the numbers that are in the tree. I have no idea what all the numbers are. So let me give you an example. So let's say that we were a university and then we stored the information about each one of our students in a database. And we wanted to look up a particular student. I want to look up Josh. And I'll assume his social security number is 555-555-5555, right? Right, because that's clearly his social security number. Actually, funny story, right? So all of you guys, probably all of you, right? Your social security number is based on where you were born, right? So mine starts with 507. My wife's is 507 because we were born about the same time. We were born in Nebraska, right? If you're born in a different state. So I don't know what your guys' start with. Maybe 50 something? No? Yes? 50 something?
They have like 506.
506? Right, so they have regions where they give out social security numbers. Well, so 2 of my children were born and they got social security numbers that were based on where they were born, which is Kansas. But my 3rd child, they found out that because they were giving out these social security numbers regionally, it was easier for identity thieves to figure out the first part of your number, right? And then they only have to guess the last part, which is a lot simpler. So now every new baby that comes, so when you guys have children, which I assume some of you will, right? They will just get a random social security number from the Social Security Administration instead of something that is less. So let's suppose that we have every social security number possible in some database, right? University of Nebraska at Kearney has accepted every student in the entire United States. Well, how many social security numbers are there? 12. There's 12 social security numbers. Okay. So it's 10 to the, how many digits are there? 9? There's 3, 2, 4.
Well, if you can,
3, 2, 4. 2 plus 3 is 5, 9. There's a billion of them, right? So let's suppose that we had stored this in a data structure, a linear data structure. So I'd have to do a billion lookups to find a particular student that's in the University of Nebraska. Okay? Well, that's a lot of lookups, especially at the end of the year when they're trying to figure out all the students that are graduating. A billion lookups for a couple thousand students that are graduating takes a lot of time. Now, the cool thing about the binary search tree, I'll come back to this, is that if we have a binary search tree, this is what we call balanced. So balanced means that basically, in general, the right side is about the same size as the left side. And usually it's within a factor, like a log factor. So it might be that the right side has twice as many nodes as the left side, but in all, it's what we call balanced. So if we have a tree that is balanced, so see if I can get it right. 8, 4, 6, 5, 7. Oh, let's see if I can get them all. 8. 12. 10. 9, 11. Trying to make this, let's see, 14. 13, 15. So if we have this tree that is balanced, right? This one's 100% balanced, right? Perfectly balanced. So I have, what, 16 nodes in here, right? 16 nodes. If I take the longest path that I have in here, is how many nodes that I have to traverse to get to the bottom? 3, right? Well, we'll make it 4, right, to take account for the top node, right? So 1, 2, 3, 4, right? Any of the paths that you pick in this one, at most, right, I have 4 nodes that I have to go through.
Wouldn't you only have 15 since we're not including 0?
Yeah, we do have 15, but we have about,
Okay.
right, we have about 16. So, yeah, you're right. Okay, technically you're right. Okay. But if we, so we had 10 to the 9, 16. It's funny how when I do the log base 2 of 16, I get 4, which was the number of traversals we have. So if we take the log of the number of nodes we have in the tree, log base 2, that's how many traversals we're going to have, right? So, right, normally it does log of 10, and if you divide by another log, you get that other log. So the number that we had was 10 to the 9. So I just went from a billion searches to 30, right? And do you see the enormity of that scale, right, that we just got? Just by the fact that we said, let's store Social Security numbers not in a linear structure where we have to search every single one. Let's store it in a sorted binary search tree, right? So if you think about this, this is sorted, right? If I do a in-order traversal where we visit left, then visit a node, visit right, if you go through and print that off, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right, all the way to 13 or 15. So the big benefit of this is we just take in a lot of data and we can search through it very quickly. right? 29 versus a billion. Tremendous speed up, right? And you might think, well, you're just exaggerating on how many students we have. And that is true. But, for example, the online ordering system that I helped create when I was working, right? When I started, we were hoping that we'd get 50 orders a month. That was a big month. I remember that. Right? It was very exciting for me, right? This is now almost 10 years later. They have had over 700,000 orders placed on this system, right? So we're not completely out of the ballpark on just some small business that does a couple $1 million a month, right? So it's not a big business. And yet they have that much data that's going through there, right? And we'll talk about how we implement this. I believe I'm about out of time. We'll also talk about some of the built-in structures that are in Java that implement these, but we're going to implement ours in C, right? So I'll show you how we're going to do that. We're going to learn about how to implement these, but I think these are really cool. I remember this blowing my mind when I learned about it because I thought it was so awesome. So, all right. So, work on your homework. I will not be in tomorrow. You can email me, but I'm not going to get back until 6 or 7 o'clock, so it'll be late before I get to any email. So, make sure you work on it today so that you can ask me questions tonight when I will actually be able to answer them.
We Skype